In the previous video, we looked at the concept of the inverse of a function, and we said that the inverse of a function undoes whatever the function does. And we also said that a function and its inverse have the same ordered pairs, except input and output are swapped. So the order of the ordered pairs are swapped. Let's take a look at what that means for the graph of the inverse. Here we're given a graph and its corresponding table of values. The table of values shows you the coordinates of each of the points in red. And this is defined, this graph, or this function rather, is defined as y equals f of x. So this is the function f. Now, if we were asked to graph the inverse, how would we go about that? Well, let's make a little table of values. Remember that the pairings are going to be the same on the function and its inverse, but the order is going to be swapped. So if this is x and f of x, we could make a table of x and f inverse of x on the inverse function. This is the way we would write that. And these points are going to have the same coordinates as this, except x and y, or input and output, are going to be swapped. So whereas -3, -4 was on the original function, we're going to have -4, -3 on the inverse. -1, 2 is going to be the point 2, -1 on the inverse. We're going to have the point -3, 2, and the point 6, 5. Now notice I'm not changing the signs of anything. I'm actually swapping what x and y are. So all the negatives stay negative and all the positives stay positive. So to plot that out, I would have the point -4, -3, and that's going to be connected to the point 2, -1. So let's draw that. That's going to be connected to the point -3, 2. So -3, 2. So those are going to be connected. And that's going to be connected to the point 6, 5, which would be up here, like that. And it's important that they're connected in the same order as their corresponding points were connected in the original graph. Now, if you look at it, you'll notice that the graph is actually been reflected in this diagonal line here. So the inverse graph looks like the original graph reflected in that line there, and that's the line y equals x. So the inverse graph, or rather the graph of the inverse, is the reflection of the original graph in the line y equals x. The graph of f inverse is the reflection of the graph of x in the line y equals x, as we see here. This is the line y equals x, and you can see, although my drawing is a little bit shoddy, that it's as if this line was a mirror. And that's what happens because we've swapped the x and the y values. Okay, because we've swapped the x and the y values, the domain of f, which is all the values x can be in f, is the range of f inverse, all the values y can be in f inverse. And the range of f, all the values y can be in f, corresponds to all the values x can be in f inverse. If you stop and think about that for a moment, you'll see it makes sense. We've swapped x and y, so domain and range have to swap as well. So as an example, if we had a function f of x that had a domain x is an element of real numbers and a range y is an element of real numbers such that y is greater than or equal to 4, and by the way, this doesn't correspond to the graph we just saw, this is another example, then the domain of f of x becomes the range of f inverse. So the range, we still have to change it to be y, but the range of f inverse would be y is an element of real numbers. And the domain of f inverse would be x is an element of real numbers such that x is greater than or equal to 4. And if you think about the fact that you're reflecting it in line y equals x and swapping x and y, that'll make sense. Domain and range need to swap as well. So that's the graph of f inverse. It's the reflection of the graph of f in the line y equals x.